page 7. When you do heat integration, what will be the good delta T min? In other words, you have any exchanger, delta T. What is delta T min? In real practice, oh, that's okay. In real practice, delta T is always greater than delta T min, okay? But what would be good minimum value? You see this table? Chemical industry, 10 to 20 degrees C. Oil refining, 30 to 40. If you have low temperature distillation, refrigeration, low temperature process, delta T min very small, 2 to 5. And you can also look at this, petrochemical, 10 to 20. So, chemical, petrochemical, 10 to 20 degrees C. Refrigerator process, 3 to 5. How about based on hot stream, cold stream, stream matches? Steam heater, 10 to 20. Refrigerant, 3 to 5. Cooling water, 15 to 20. Flue gas, steam, and so on. All right, let's come to the real thing. What is the pinch point? What is the significance we're trying to do? Here is one example. You want to heat up a cold stream 60 to 180. Capacity flow rate m dot Cp. Mass flow rate times heat capacity, kilowatt per degree C. What if this 3600 is m dot Cp delta T is 30 kilowatt per degree C. 180 minus 60. This is 3600 kilowatt. Cold stream, stream 3, 30 to 130, 22. 22 times 100. Hot stream, cool it down, 140 degree, 20, 140. Heat added to the system is positive. Heat removed from the system is negative. Heat removed from the hot stream, 2800 kilowatt, so it cool down from 180 to 40. Stream 4, cool it down by 110 degree. Okay. 40 times 110. Total heat removed 4400 kilowatt. Now, let's take a look. watt is cold stream. 3600, 2200 cold stream need 5800 kilowatt. Hot stream release 7200 kilowatt. A common sense might think the difference between the two. If you transfer all the heat released by hot stream 7200 to heat up cold stream, you might have surplus of 1400 kilowatt from hot stream. That is wrong. That's wrong. The common sense, all the heat released from hot stream, use the heat of the cold stream, there's a surplus of energy. Why is that? Why it is wrong? What was the topic we covered last hour? You have ignored what? You have ignored delta T mean. Okay? Just thinking, ignore delta T mean is not reality. Before today, do you think that way? It's a sophomore. It's a senior beginning today. You're more small. You cannot do that. All right. Now, the way we do it, we choose the temperature. If hot stream temperature, if delta T mean, okay, let's look at this example. (10° C), okay. 10° C, okay. The way we do it, hot stream, cold stream, you must maintain minimum delta T mean 10° C. And there's an intermediate temperature, 5° here, 5° here, intermediate temperature. How do we find out for this heating a cold stream, cooling a hot stream? What is the minimum heating cooling utility required? How many kilowatt? Okay? So, look at the next page. We're going to do it by hand. I teach you how to do the pinch analysis by hand. First, cold stream. You write down the temperature, 60 to 180, 30 to 130. Hot stream, 180, cool it down to 40. 150, cool it down to 40. Now, this temperature is between hot and cold. We call that interval boundary temperature. You can understand that in a minute. For cold stream, hot stream, hot, cold, intermediate. So, you add 5 degrees C here, you minus 5 degrees C here. So, for cold stream, you add 5 degrees C. $60, $65, $180, $185, $30, $35, $130, $135. Hot stream, you minus 5 degrees C, 175, 35, 145, 35. Instead of working on the real stream temperature, let's define this intermediate temperature. If you know this temperature, say 100 degrees, you know hot stream is 105, cold stream is 95. So, you use one single temperature to represent hot stream and cold stream. And both streams meet the requirement of delta T mean, 10 degrees C. Yeah.
So for cold stream, you add 5.
Cold stream, you add 5 degrees.
So, and then you said it's cold stream should be subtracted by.
This hot stream, you minus, right? Wait a minute. Cold stream 130, 135 is correct. Cold stream, you add 5 degrees. 130, 135, 30, 35, 180, 185, 60, 65.
It says above that cold stream you subtract.
What?
I think you inversed it. Because you said above, like in here. Like in this diagram. It says cold stream subtracts with that.
Well, I haven't touched the diagram yet. We'll do that in a minute. I only change the given stream temperature. Given stream temperature.
Now, every time you do this, you set your own delta T min, like it's an arbitrary.
From the previous table, minimum 15 to 20, right? So in this problem, it's assigned 10 degrees. So heuristic value is in the previous table. Anything else? Okay, let's go. So now the next thing is, let's arrange this intermediate temperature. You know one value, you actually define both hot and cold. Okay? So, from high to low, 185, 175, 145, 135, 65, 35. Combined together, arranging from high to low values. Now, you put this value, you have 6 value. You look at this table, you draw 6 horizontal lines. 185, 175, 145, 135, 65, 35. So you draw 6 horizontal lines. The next thing is you draw a vertical line. On the left, half stream. To the right, cold stream. You put down the string you have, half stream 1, half stream 2. Cold stream 1, cold stream 2. Now, this 185 for half stream is 190. Cold stream is 180. 175, half stream 180, cold stream 170. 145 is 150, 140. 140, 130. 70, 60, 40, 30. No, you could. It's not necessary, but you could. 180 is the real quotient temperature. 180 is real hot stream temperature. So 170 is not the real cold stream temperature. 150 hot stream real temperature. 140 is not. You can draw a parenthesis, but you don't need to do it, not necessary. Okay? Now the next thing is, hot stream 1, cool it down. 180 to 40. Hot stream 1, 180 to 40. 180, 40. There's a real temperature. Here is intermediate temperature, right? So, I draw a vertical line, hot stream cool it down. 150 to 40, hot stream 2. Hot stream 2. You get it?
No.
No. You better get it. Okay, cold stream 1. 60 to 180. 60 to 180. Cold stream 2, 30 to 130. 30 to 130. The next thing we do is, for all the hot and cold, you write down their capacity flow rate, 20 kilowatt per degree C, 40 kilowatt. Cold stream, 30 kilowatt and 22 kilowatt.
Is this in relation to the starting temperature
starting temperature, quotient going up,
Has a,
30 to 130, 60 to 180.
and it has a heat capacity of 22 and one has a heat capacity of 30.
Yeah,
Okay.
because we want to do calculation, we need to use this value. You get it? That is from your table, from this table, capacity flow rate. Now, we want to do heat integration. Let's combine the two hot streams together. We call it composite hot stream. What are the heat available by cooling down hot stream? Available heat. Here, combining two cold streams together, composite cold stream. To heat up this cold stream, what is the required heat? Okay? We want to do that for every temperature range. First, in this temperature range, available heat, 0. There's no hot stream. Right? Now, hot stream cooled down from 180 to 150. 30-degree temperature drop times 20 kilowatt per degree C. Hot stream give out 600 kilowatt if you cool it down from 180 to 150. Now the next temperature range, you see two streams. Both temperature drop by 10 degrees C, multiplied 20 plus 40, 60, times 10, 600 kilowatt, available by both hot streams in this temperature range.
But both still have the,
In this temperature range, 150 to 140,
it's still 30 times 20.
30 times 60, because you have two streams.
So it's not 600.
30 times, wait a minute, 10 degree times 60. 10 degree, sorry. Now, here's 70-degree temperature drop times 60, 4,200. 70-degree temperature drop, two stream times 60. 30 times 60, 1,800. Now, remember you put a number in the middle between the two lines, okay, in the middle. What does cascade heat mean? If you go from high temperature downward, what is the total amount of heat available from both streams? This time, you put a number directly on this line. Put a parenthesis there. Add them up. Accumulated. So, this 7,200 is exactly what I had before, 7,200, right? And the sum of 36 and hot spring, 28 and 44. We took care of hot spring for now. Is there any question? Now, coaching. Heat it up, coaching 1 by 10 degrees up times 30. It requires 300 kilowatt. Put that in the middle. Here, 140 to 170, 30 degrees times 30. 900. 130 to 140 times 30, 300. 60 to 130, 70 degree temperature rise. Here, you got 2 streams. 30 plus 22, 52 times 70, 3640. 70 degree temperature rise times 52, 3640. What does that mean? You want to heat up both streams up 70 degrees in this temperature range. Required heat is 3640 kilowatt. Lastly, coaching 2, 30 degree temperature rise times 22, 660. Do you understand this? Cascade heat. Cascade heat. So, I put 300 here. Required heat 1200, 1500, 5140, 5800. That is the number we had before. Cold stream, 3600, 22,000, 2200. The sum, 58. Now, here comes the heat integration part, exciting part. You call this grand composite stream. We are going to look at both hot stream and cold stream together. This color is called net heat. Now think about it. You want to heat up cold stream 1 by 10 degrees. There's no heat available from hot stream. So, A, available heat, B, required heat, C equal A minus B. Zero, 300, you're short of 300 kilowatt. If you can transfer all the heat from hot the heat of the cold stream, net heat, 600, 900, minus 300. 600, 300, 300. 40, 200, 36, 40, 560. 1800, 660, 1140. We're getting there. Now, you look at here, 0, 300, 600, 900, 600, 300, 40, 200, 36, 40, 1800, 660. Cascade heat is the same concept. Minus 300, minus 600, minus 300. Oh. Wait a minute. Yeah, it's correct. 260, 1400. Now, what does this tell us? In order to heat up cold stream, especially cold stream 1, to reach the target temperature 180 degrees, the heat deficit right here. Hot stream cannot provide. You look at this column, find the largest negative number heat deficit. Look at this column. The largest heat deficit is right there, which happens to be the sum of both. Hot stream cannot provide this heat to heat up a cold stream. What do? I move this to the top. This I use external steam heating. How many kilowatt? 600 kilowatt to cover this heat deficit. Total heat deficit. Right? I use this 600. Now.
Is that now a positive 600?
Yeah, positive. You change the sign because you provide a heat. Now, with 600, here comes the exciting part. Watch the arrow, okay? I use different color. Maybe I should longer line. 600 provided from externally cover this heat deficit. What's remaining 300 cover this heat up cold stream 1 from 170 to 180. And this heat surplus, let's do it. 0. This 300 covered that heat deficit. There's no more extra heat. That's okay. Now, This heat surplus. This is wonderful heat surplus. Positive. 0, 300, 300. 300, 560, 860, 860, 1140, 2000. This is heat surplus. What does that mean? This is external cooling utility. You must use cooling water to remove this heat. So for this problem, utility target minimum heating equal 600 kilowatt. Minimum cooling (2,000 kilowatt). This is different from 1400 wrong. You see here? Now, here comes the most important point. What is a pinch? Where is the pinch? You look at here, there's a wonderful zero here. You draw this line above, so pinch temperature equal hot stream, cold stream at 150, at 140, hot stream 150, cold stream 140. What is the significance of this temperature? Above the pinch, process is cold heat deficit. Below the pinch, process is hot heat surplus. And this is what we call pinch point. Pinch point exists only if the process needs both heating and cooling utility. Okay? And this part in the heating. How do you remove those heat surplus? cooling. Okay? What's special? Above the pinch, never use cooling water. That means above the steam temperature, 150, 140, never use cooling water. You do not put a water cooler here. Okay? You won't put a water cooler, you make the cold stream colder. Right? Here, you already got his surplus. You put a water heater, steam heater here. That's no good. So, this is important number. That is important number. Now, go to page 10. If you did not write this properly, I got a page 10 here. I have not covered this column purposely here. We'll do that next lecture. Watch it. QH mean, QC mean. Be larger. You see here, pinch point. This number is intermediate temperature. Hot stream, 5 degrees above. Cold stream, 5 degrees below. You start with 600 external heating. Minus 300. That is this number. Minus 300, 300, 560, 1400. 60 minus 600 minus 300. There's 300 going downward, and this is 0. This is pinch point. Here, all his surplus, you require cooling. So, what is importance of pinch point? Before we even design a heat exchanger network, we know what is minimal steam do you need. What is minimum cooling water do you need? And where you do not use here above the pinch. No cooling water, only steam.
This would be in a series of reactors that operate at different temperatures.
No, you give me a set of hot stream, cold stream, I do an analysis. Okay? Below the pinch, process is hot, no steam, only cooling water. Do you get it? So, I'm the recruiter. Are you learning pinch analysis? Tell me what's the pinch point. You.
It's the temperature at which cut off cooling water versus.
No, you should start with if the system requires both heating and cooling. Okay? And we can find a temperature above which the process is what? Cold, only require heating utility. Below which process hot, only require cooling utility. That's a pinch point. That guarantee you to use minimal heating and cooling utility. You get it? All right, go home.